To the last stretch of the conference. I want to remind you that if you haven't already signed up for membership to the
I've been experimenting on this for about 18 months now. Recently I had a small amount of success. My VTA replica worked for about 2 minutes only, less than that, probably a minute. Yes, I'll get closer. My VTA replica functioned for about 1 minute, and or probably even less than that. But it didn't even give me enough time to go and get a test meter to do any measurements. It just functioned. By the time I came back with a meter, it had stopped. Now that is the big problem with the Floyd Sweet VTA. Sweet himself has had these devices working for many months, but he has the golden touch. He's a long-time engineer, well practiced in machinery, electronics and so on, and although he's now over 80, he has the golden touch which is necessary to get these machines working. This talk's divided into two sections, two parts. The first part is given by myself and is devoted to the Floyd Sweet VTA, as I've just said. And the second part is given by Don Watson, who's here, who incidentally is no relation. I'm not his father, and he's not my son, as some people have suggested. Don Watson arrived at his VTA, in inverted commas, completely independently of Floyd Sweet, purely due to his own experimentation. And all the information which he's got has been arrived at by his own work, and from what he found many years previous to the publication of the Floyd Sweet VTA stuff. So that it's really an independent approach. I met Don Watson here first when we all came together in this conference up in the retreat, and he was able to illuminate several areas of the VTA which Floyd Sweet had left obscure or purposely just had not disclosed. Now it's clear that some of the information which Floyd Sweet had given me, although not inaccurate, doesn't contain the full truth, or the truth is contained in it, but so heavily masked in rubbish and peripheral material which is no importance that it's very difficult to extract the data. But nevertheless, my aim is to actually tell anybody who's interested how to make a VTA. They can go away and do it. It's not a cookbook on how to make a VTA, because there are so many variables and so many parameters that it's actually very difficult to get the thing to work. And it's a question of experience. You've got to try, and in the process of time, it may take you a month or two, you'll get it going. Now, the VTA the title VTA stands for Vacuum Triode Amplifier. Strictly speaking, it's nothing to do with a vacuum. It's not a triode, and it's really not an amplifier. But this name originates from a theory which Tom Bearden had probably in about 1986, which relates to was his idea of how the VTA functioned. This was in the early days when Floyd Sweet was still experimenting on it. I suppose the vacuum may be attributed to the zero-point energy. And the zero-point energy is something which we've heard quite a lot about in this conference. So possibly you can regard the energy as being sourced by the zero-point energy, and so the vacuum thing it's just possible that you could call it a vacuum, but it's a misleading name. It would be better, in fact, to call it a magnetic amplifier, because it's a self-exciting magnetic amplifier. Now, the magnetic amplifier hasn't been around for some while. It was used a great deal during the First World War and the Second World War, and it is, in fact, very rugged. I won't go into the theory of magnetic amplifiers. It's possible to find it in the literature for those that are interested. The difference between the magnetic amplifier and the Floyd Sweet device is that the magnetic amplifier requires, like any amplifier, a power supply, whereas Floyd Sweet's device is self-exciting. That is to say, it sources its own power. Now, we don't know where the power comes from, but of course the zero-point energy is the favorite buzzword at the present moment. And I think probably that's a good start anyway. But we really have no idea how the device functions. The device consists of a barium ferrite slab, which... Can we just have that on a minute? Which you can see here. Now, I'd just like to say here that there are several versions of this device. Floyd Sweet has operated a twin magnet device or a single magnet device. Now, he has told me this is the simplest way of doing it, so just use one magnet. But I'm not too sure. I suggest anybody who wishes to try the experiment, in fact, uses two magnets, face-to-face with the on the north-south way, in other words, in attraction mode. Now, this is a magnet which is 6 inches by 4 inches by 1 inch thick. It's barium ferrite, as I said, and around this magnet are wound coils like so. If you go downstairs in the equipment room, you'll see my version of this. The coils alone are there. I couldn't bring the magnet over. It wasn't conditioned anyway, but I couldn't bring it over because magnetic materials, especially for transatlantic flights, are protected items. Yeah, not protected items. You know, you can't put them in baggage and so on. They won't allow you to do it because it might upset the compasses or something like that. So that basically I just bought the coils. Now it turns out that Don Watson has a magnet of the same size but half the thickness down there, which will give you an idea of what the magnet is like. Returning to the barium ferrite thing, it's absolutely essential that it's barium ferrite. Yes, sorry, the field goes straight through it. That's north on this face and south on the underface. So the whole thing is like that. This is when you buy it. But as I shall point out in a minute, the process of conditioning changes the magnetic configuration considerably. And this is the important thing. Due to shortage of time, I'll have to sort of accelerate the procedure a bit.
Are these in the proceedings, these diagrams?
These diagrams are in the proceedings, but what I'm about to say now is not completely in the proceedings, because I've modified my views somewhat. It's so fluid, this business, that it's changing all the time. Now, I'll get on straight to the conditioning thing. We know that it's possible to do this with two magnets. The coils are wound on the 3 axes there. Note the names A, B, and C coil and the way in which they're wound, because I'll refer to those. You see the structure of the machine there. As you go down, as I said, into the equipment room, you'll see this things like this down there. This wire is 19 American gauge, which is 1 millimeter European. It's the normal standard insulated copper wire.
What gauge was that?
It's 19 American gauge, roughly, approximately, 1 millimeter. Now, the conditioning. Sorry.
Is it a needle? Is it tinned? Is it enamel?
Oh, it's the usual enamel instrument wire, magnet wire, I think you call it here. It's polyurethane covered because it's easy to deal with, that's all. Any enameled copper wire. Okay? Now, the conditioning of the VTA. The conditioning of the VTA consists in a process of controlled demagnetization. It's done by applying a large high-energy pulse to these coils which are wrapped around the magnet. Now, let me just illustrate a little bit exactly what happens. This coil, the A coil, where is it? That A coil has got about 500 turns on it, and it's fine enameled copper wire as usual, instrument wire. The resistance for that in my case is about 70 ohms, and it's round with about, I think it's about 30 gauge, 28 or 30 gauge. This is the English gauge, so it's very similar to the American gauge. It doesn't matter, it's not important, but it should have about 500 turns on it. The impedance at 50 or 60 hertz should be reasonably high. Now, these coils here have got about 100 turns on them, The C coil and the B coil have 100 turns each. I say approximately because it's important to get the length of wire the same rather than the number of turns. In other words, we're more interested in the resistance of the wire than we are in its inductance.
On B and C.
On B and C.
So they're all about 500 turns, or?
It's about 100 turns. On B and C is 500 turns. A is 500 turns. B and C is 100 turns each. roughly. Because the perimeter of the C coil is greater, so it's about 115 on one and about 90 on the other. When you come to do it, best to get the same length of wire to give you approximately the same fairly accurately the same resistance, and then wind it on. Not very accurately. I would say they should be within about 5%. Sorry?
You're talking about resistance, so the resistance should be the same on A, B, and C?
No, just B and C. The A coil has got many more turns, and it's sort of out of this equation just for the minute. I'll tell you what the A coil is for. The A coil is the excitation coil. If you ever finally get it working, that's the place where you put your AC input signal, which is a small, low-energy signal which sets the thing into oscillation. Now, the process of conditioning consists of connecting these coils in parallel. The B and the C coil, The B and the C coil are connected in parallel, start to start, finish to finish. And a 500 or so joule pulse is applied, one single pulse at a time. You'll have to do this because the capacitors take so long to charge up. But you need to do this with electrolytic capacitors, some sort of thyristor triggering device, and some sort of detector for the zero crossing of the 50 hertz, in our case, European standard, but 60 hertz signal, which is applied on to the A coil. I'll go through that again. What you've got is this. You have a 60 hertz, 1 amp current flowing through the A coil. Okay? From some source. Transformer will do. Doesn't matter. It doesn't have to be 1 amp. Be 2 amps or half an amp or something of that order. The current is not particularly important, but it should be significant. Say about 1 ampere through the A coil. Remember, the resistance of the A coil is of the order of 50, 60, 70 ohms. Now, during the... If you... it's difficult to draw it from here, but if you... the AC waveform coming in on the A coil, it's important to, at the point, the maximum peak point of the AC signal going in on the A coil, it's important that you synchronize the firing of the pulse. It must be coincident with the peak of the AC signal going in on the A coil. It must be. You must make sure that it's synchronous. If it's out of sync, it won't work. Sorry?
Can you say that one more time?
Yes. You've got an AC signal going in on the A coil, and you have the capacity to pulse the B coils. You must synchronize the pulse on the B and C coils, which are connected in parallel, with the peak of the AC waveform going in on the A coil, which is AC, which is 50 hertz. Sorry?
Voltage or current?
Voltage.
Positive, negative.
Pardon?
Positive or negative?
I'll come to that in a minute.
How big a pulse?
Well, I'll come to the pulsing too. The pulse is a good pulse. It's about 500 joules energy. Now, you should arrange the direction of the pulse to be opposite to the signal going in on the A coil. In other words, if it's a positive peak, if the magnetization field is round here on the A coil, you should arrange it to the positive peak. There's a negative going pulse. The importance of this is it's not actually so important with this configuration, but when you come to see Don Watson's configuration, which is different, it's very important that you get the directions of the pulses correct. You'll have to find out whether it's whether it actually is important in your particular configuration. In mine, I had to make sure that the pulse was negative going when it was positive on the A coil here. And the reason for this is it depends a lot on which way round you have that magnet. If you've got to make it so that when the current direction of current flow through here is in opposition to the magnetization of the magnet. In other words, the flux direction from the A coil is downwards if the magnet is polarized upwards. And you can get that from the usual magnetic rule. Which way around the polarity's got to be. It's got to have the opposite polarity to the magnet. Now there are certain variables in here which are not understood. And all this is a question of experiment. It's not possible to define all these things. As I said at the beginning of it, it's not a cookbook. You will have to experiment. It'll take you a lot of time, but it can be done with playing. You've got to play around at it. Now, let's come to the size of the pulse. The pulses are the order of 500 joules. My capacitors are 450 volt working, and I have 0.008 farads, in other words 8,000 microfarads. I've got 8 of these capacitors, 8 1,000 microfarad capacitors run in series. For purely practical reasons you need to do this because the peak pulse current is several hundred amps. And if you don't do that, you'll destroy the capacitors. They won't last long. You've got to have a parallel combination to try and share the peak current load from the capacitors. Sorry? No, they're all in parallel. Did I say series? Sorry. I meant the parallel combination of capacitors. Yeah, right.
You said the peak amperage would be how much?
It's about 300 or 400 amps. It depends on the resistance of the wire on here. You've got 2 in parallel, and how many turns you put on. I think it's about 350 amps on mine.
What's the voltage?
450. But that's peak. That's the max. The pulse voltage will be 450. The A coil's just got this 60 hertz signal at 1 amp going through it, maybe 6 volts, 7 volts, 8 volts, depending on its resistance. The pulse, you've got to arrange in this particular configuration, it doesn't matter too much. But I should arrange, like I said, that the pulse has the opposite direction to when you actually come to do it.
Opposite direction.
No, the A coil, you can define the A coil precisely. You've got to arrange the flux path from which is produced by the current flowing through the A coil to be opposing the magnetic flux direction when you do the pulse. But which side you put the pulse in on, I haven't found any difference. But you'll have to experiment on it. It may be that there is a difference, but there's a lot of things which require looking into.
Now, you put this pulse in the A coil. I might have missed that. You probably said that. You put the pulse in the A coil.
No, you put the pulse in the B coil, B and C coil in parallel.
Both of them.
Both in parallel, together, absolutely together. Yeah, so the field the effect of the field on the B and C coil is to produce a diagonal flux path across the magnet like that, or in this direction, depending upon which way the pulse has gone in and you've wound it, which is the start, which is the finish, and so on.
400 volt pulse?
400 volt pulse maximum. I'll tell you about that in a minute, how you've got to do it. The important thing about it is this. That when as a result of putting these pulses in on the magnet, you find it partially demagnetizes this. Now, when you actually try it, you'll find that it is impossible to demagnetize a barium ferrite magnet properly. If you try, you find that you don't just produce something without any magnetic flux in it, but it introduces mayhem in there. There are millions of poles, and distribution is enormously complicated. The thing you have to do is to bring about here in the central portion, a bigger area as possible, but within a 1/4 of an inch boundary here, all the way around, an area where the flux density is reduced from the normal 3,900 or so Gauss, which you get with a barium ferrite magnet, down to about 30 or 40 Gauss. And it's got to be reasonably uniform, and that's what the whole key to the initial conditioning process is. If you don't get this configuration, you end up with, Sparky Sweet says it just won't work, but my feeling is that it works partially but inefficiently. Now, there's enormous reduction here in the pole strength, and when you have this, you have an area here, and you have a defined border around here like this. Now, somebody mentioned, he asked me what amplitude of pulse you need. You have to start low. When you do it, it's not just one pulse you need, but several hundred. The process of preconditioning takes about an hour. And you start off with maybe 100 volts on the capacitors. You zap it with the pulse in synchronization with this AC signal. You zap it with the pulse and have a look at the pulse strength. And you'll find that it starts off with a patch in the middle and it slowly grows outwards as you increase the amplitude of the pulse. Now, it's important not to overdo it, hence the importance of doing it in steps. So that's the basis of the pre-magnetization.
Was that slab magnetized before you put
Yes.
the on it?
Yes.
Do not take it through the loop. Good. It merely
So I'll show you, if you're going to put on the next thing here. That's right. Here's a type 5 strontium and a barium ferrite curves. I'll come to why I put strontium there as well in a minute. You see that the normal remnant flux is about 4,000 Gauss. Now, with barium ferrite, the knee occurs at about 2,000 Gauss. This is Webers per square meter here. Now, as you see, at that point, after the knee, it descends very steeply. And this coercivity here is 140,000 amp turns, roughly. You don't take it through the loop, but what happens, because if you're up here and you demagnetize a barium ferrite magnet, it recoils back up here again. But if you go down here after the knee, you'll find that if you apply the pulse effectively applies a demagnetizing force in this direction, it goes down here and it recoils up to somewhere here. And that recoil line, are no longer parallel like they usually are when the magnet is running in its proper mode. So in other words, this slope is unknown. And this means that the remnant flux, which has got to be about 30 or 40 Gauss, you have to find out what pulse amplitude you need to get it to be like that. And it differs from magnet to magnet. It differs from the size of the magnet, the volume of the magnet, the manufacturer, and everything. Get two magnets of the same manufacturer, they're different. So something which has to be found from experiment. Now, having established this uniform magnetization, well, running over a bit on time. Got somebody else? Having established this 39, about 39 and 40 Gauss on there, the next problem is the real important one. This is the key to the VTA, at least we think so. You have to apply, either at this stage or at the beginning before you try the magnetization. We haven't decided clearly what it is yet. You have to make the magnet the dielectric of a capacitor. Put two plates either side of it and apply 15,000 or so volts, maybe 20,000, maybe 10. You've got to apply an electric field across the capacitor. The electric field presumably puts the barium atom, my theory, puts the barium atom in an excited state. It's metastable, this state, rather like, as Don Watson mentioned, rather like phosphorescence. It goes up into this state where it sits there and stays there. And this metastable condition is the state in which the magnet must be for it to function. Now, the important part about it is this. This is the crucial part. If you demagnetize a magnet this way, you will get several sort of circles or bubbles. Yeah, that's right. Several sort of little circles or bubbles, like magnetic bubbles, on the magnet surface. If you bring a small magnet, permanent magnet, near them, you'll find they're fixed. They move a bit, but not much. What you have to do is to produce a mobile magnetic field. The magnetic field will respond. When it's conditioned, the magnetic field will move across the surface of the magnet rather in the way as though it were mercury under the influence of a magnetic field. It'll move easily and quickly. And that's brought about by this electrostatic field. Why it happens, how it happens, I don't know. Sparky Sweet has partially told me this information, but not fully. I've had to find it out for myself. In fact, I found it out from Don. When I had my machine working temporarily for that 1 minute or so I mentioned, actually I think it's probably less than that, for a very short space of time, the reason why I had it working was it transpired, and I'd forgotten this, that I'd done exactly that. I'd used the magnet as a dielectric. I had done some subsequent experiment, which I can't recall what it was. It came to nothing. And then I used the magnet for this conditioning process, and the thing burst into life amazingly. And I just wasn't expecting it. And that is the key to the whole business.
At what time is that done? Is that during the conditioning process?
No, this is the thing you've got to find. Yes, it's part of the conditioning process. Sparky Sweet seems to interleave it, as far as we can tell. He does a few pulses, soaks it, does a few pulses, soaks it, does a few pulses and soaks it. Mine, I did it a week before. Don's got, when you come to hear Don's section, he'll tell you more about that. But you've got to experiment. You just have to experiment. I can't give you a decisive answer because I don't know.
How long did you leave the capacitor?
Well, mine was on for about an hour, but it may only take a few seconds. So it probably does. You may find a pulse is sufficient. But it's extraordinary. Evidently the magnetic flux, field which you apply in the form of the pulse can't excite the barium atom itself. But the extra high voltage EHT you apply to it, 20 kV, does manage to succeed in doing this. It brings the barium atom into a state which it can't normally be in from a magnetic flux. It requires the electric field to bring about this change.
Do you do that while you apply the excitation field?
You can, and that's probably a better way of doing it. I mean, there's some sort of experiments I can suggest, which I haven't done, is to, instead of having that A coil on there, which applied the 50 hertz, is to
considered using a capacitor and stress the barium atom while it's in operation, keep it at the metastable states.
Yeah.
That sounds like a good idea. Because they do die, and this because it jumps out of this metastable state.
At resonance, and you put the coils in series and drive it to resonance.
Right. Absolutely. There's several different, we try these experiments. This is what I'm trying to say. Trying to make all this stuff public domain so people will experiment and find their own combinations and conditions. All that we've done is touched upon a couple of the obvious ones. Yes, sir.
The electrostatic is done after the electromagnetic condition?
It can be done before. In my case, it was done before. It's possible that it can be done afterwards. I suspect that it's better to be done in between, in the middle. All right? In other words, you'll have to find out by trial and error.
What if instead of using a rectangular magnet, you use a circular one and have these conditioned with radio?
You could do that. I mean, the circular coils would be one of the things. Well, I think Don's coming on now. I'd just like to make one very short comment before Don comes on, and that's it. That is a couple of provisos which have been introduced, which somebody here, I don't know whether in this room, has mentioned to me, and that is some Russians apparently. I don't know any details. Some Russians have been involved in doing these experiments, similar experiments, is all he said, and they have reported some negative health effects from these mobile magnetic fields. It could be carcinogenic or something like that, somebody suggested. Now, with the flux densities we've got here, which is only about 10 or 20, whatever it is, more than the Earth's magnetic field, maybe 60 times. I don't honestly think that it's much of a hazard, but you'd be well warned not to sit day and night in front of one of these conditioned magnets experimenting with it, and take it easy, do a few hours at a time and then leave it. So I just pass that on. Stefan? No, some Australian chap told me. Okay, fine. I'll pass it on to Don Watson. Oh, yeah.
Thank you.
Okay. First of all, this is probably the most people I've ever seen in my life in front of me that I'm speaking to at one time. but I'll give it the best that I can here. The processes are normally very similar between what Mike is talking about and also what I've experienced in my research and studies on this. Eat the microphone, okay. In the experience, what I normally do is I'll take a coil that I use for the condition, and this is something that's not necessary. This is just something that I experimented with, and I feel that it helps me. Is during the conditioning process, I'll fire one charge into the magnet, and I'll look at the magnet for impurities. One of the ways of the impurities, if I'm getting spurious amounts or bubbles, or should I say regions of reverse polarities across the face of the magnets itself, then I have to go back and start over again, remagnetize the magnet conventionally, and start this process again. This is how I look for a pair of magnets in order to balance them, a balanced set of magnets. Okay? After I do this, and I do get a set that is working properly, I leave it in the state that it's in, and then that's when I go to the electrostatic stage. Now, let me give you a little bit of story on how I got to this electrostatic stage. I've got experimentation that I have done myself on a completely and totally foreign configuration of using barium ferrite magnets. I use the round cores with one feeding through the other like a chain link. And in utilizing that, the experimentation and this electrostatic charging that I'm doing here is what I did on mine, which goes back to the age of 15, 16 years old. So I would say that's a good 15 years from here, past. Now, once after this is done, and please don't ask me what this does, there is theories, there's several theories to this. All I know is that once this here is done, I go back to where I had the bubble and find that the bubble that I had just placed into the magnet itself is easily movable by external forces. Okay, first of all, the walls, or the transition point between north-south, is very hard to move. You bring an external magnet to this, and it just doesn't want to move anywhere. It's real stiff. After the electrostatic stage, I found that the bubble has loosened some and making it a lot easier, whereas if I had a magnet I brought across near the magnet here, I can now bring it to a distance of here to achieve the same effect.
How do you observe the motion?
There's a green plastic paper that I get from a magnetic company. This is called MagnaView. What this does is it's like little tiny filings of metal particles sandwiched in between two sheets of plastic, perhaps, or there's another substance on the back that I'm not familiar with. But when this is placed upon a magnet, and I have one here, if any of you, if you want to pass this around briefly, if anybody wants to look at this, by moving the paper around, you can see the bubble that is in this magnet here in this configuration.
If I make a suggestion, be careful about getting it close to a credit card.
Right. If you get any credit cards, keep the magnet far away from you, especially if you use your room key and put it in your shirt pocket and you're up here, you won't get back in your room. Now, as Mike was describing before, the center portion of this does lose its gauze, or it loses its field slightly, during this process or in the beginning of the process. Now, whether the techniques that I'm using to make this happen, whether it works in that defined order or whether a different order can be done, I don't know, because this is the way I generally did the cores I used in my experiments.
You use the capacitive discharge.
Right. The passive discharge, which was on the other slide that I had up here, I put this one up here to help Mike be able to present his in what way that the static was done. He may have done his a little bit different, but basically it's the same. Okay. Now, this is where we get to the coil configurations of the VTA duplicate. Now, here's one thing about this situation. The one I duplicated uses a small set of magnets, like this that I'm holding here. I did not go to the 4x6 plates like he did. I used a smaller version of it. The effects that I've got here was at one time 67 volts. I'm going to say slightly less than 1 amp, but it did power a light bulb that normally ran on 120 volts. That you know that the input, which are a 9-volt battery going into 555 timer circuitry in order to induce the sine wave, did not, in fact, cause the light to light up. Bifilar coil arrangement, I used the parallel bifilar arrangement, which this is a simple schematical diagram here showing the bifilar coils on the output section, which is this coil that is along the axis of the magnet fields. And this one here being the input coil, which is running across 90 degrees perpendicular to the output coil, sandwiched in between the two magnets. You can bring it up just a little bit. At this point, and I probably got about 30 seconds left here, is I inject an AC signal into this output coil at the same time that the conditioning coils, there's an example of one of them here. This is a conditioning coil used. It sits on the outside of the magnets themselves. And feed the pulse, of course, on the same cycle rating that Mike Watson was talking about, except he was talking about positive. It doesn't matter if it's positive or the negative pulse, as long as your polarities is right, and you have to kind of play around with this to find out. One of the ways is by looking at the transitional lines on the original bubble that you have formed in it for increase in width or decrease in width will tell you if your polarity of your AC coil is correct when you induce the charge. The charge has to be done several times, and there are instances where you have to take, and in this case you've got a solid magnet, and you, by certain tilts and turning the magnet around inside this, giving it several different charges. Of course, anytime you make one tilt, you want to make sure that you give it a charge on the opposite tilt as well. And once that you have the thing running, there is some rumors that you should be able to, either on the input coil or the output coil. I've only tested it one time, but I felt that it was because of machinery I was around that was causing it, was a very small AC signal that was being present in the unit with no input whatsoever when the unit is not running. Okay.
Just a question on this coil assembly. I see there's a bipolar wound coil there, right?
The output coil is the bipolar wound coil.
Okay, and is there something inside of that one?
This coil here being the input coil is across the axis, looks like in this configuration, and is placed right inside of the output coil itself. Instead of using the coils on the outside of the unit like I've seen some configurations, this one is one single coil that's placed inside the unit. I've seen a picture of what gave me the idea to try to do this one here is I saw a photograph one time of a magnet that had no external coils on the outside. So there had to have been another coil somewhere, so I would say that it was in the inside of the unit.
How many turns are there?
This one here is roughly 900 to 1,000 turns of number 28. This one here is about 300 turns. And this one here is 22 to 18 gauge is what I'm using for the output coil.
Your coil assembly, does that see the south pole from the top magnet?
Which coil is that? This output coil?
Coil assembly sees the south pole from the top and the north pole from the bottom.
Well, the north pole, each magnet is north, south, and then north and south in the attractive mode. So this is like an exploded view where you can sandwich these back together to see how this coil assembly is. By taking a for instance, if you take the magnet and suspend it from a string, it'll align itself. The north pole here will point south. How much time? I believe I've used it all up.
Just on your windings, I got the input coil was 900 to 1,000 of 28. And what was the output coil?
The output coil is about 300 to 350 winds of number 22 to number 18.
Not divided by 22.
The conditioning coil. Let me do this, since my time's run out here, and I'm going to have to get off of here. If any of them want any other information, we can kind of group together at another location briefly. Pardon?
Your address put up?
Oh, yes. I'll leave this up here and then I'll get down.
Speak it right into
Permanent address here. This address is always good. The mail will always reach me if you want to do any correspondence, and I'll be more than happy to send you any information that I can in order to help. Don Watson, 4356 Highland Street, Lancaster, Texas, 75134-1422.
Can you be reached on the internet?
No, I cannot. Not at this time. SA Technologies is a company that I was a shareholder of, and arrangements of that, of selling the shares and other agreements, that I will be leaving the company, but I'll still correspond through the company and still have friends there as well. So this would be the best address right here. This mail here will probably be delayed a week. Right now, at the moment, I'm in California doing some experiments.
Where do you buy your barium ferrite magnets?
Good question. I haven't been able to find barium ferrite except through other sources of people, and especially some here that have been able to tell me where they can get them. It's mainly been overseas. What I used to do is go into a magnet company there in Dallas with a voltometer and go through their magnetic supply until I find the highest resistance, which is up and beyond 20 megohms.
Did you experiment with the strontium ferrite magnet?
No, I haven't. Well,